We're about to start the second session on MPC. So Sihang Pu and Marshit, I hope you're in the room. Okay, good. So the second speaker can already get his microphone while the first speaker is speaking. Okay, good. So we will start with the first talk of the session. So Arpita Patra will speak on perfect asynchronous MPC with linear communication overhead. This is by Itai Abraham, Gilad Asharov, Shavana Patil, and Arpita, who's giving the talk.
For the introduction, as mentioned, the talk is on perfect asynchronous MPC with linear communication overhead. And this is joint work with Itai, Gilad, and Shravani. OK, so our concern is communication complexity. And as all of you know, communication is an expensive resource in cryptography and distributed computation. Consequently, a huge amount of research has been devoted towards characterizing the volume of communication that we need for various cryptographic and distributed computing tasks. And in this work, we focus on the central primitive of secure multiparty computation. So over the years, MPC had been studied in various settings based on the network we consider and then the adversary as well as the security we want to demand. For instance, we can opt for a synchronous or an asynchronous network. The adversary can be computationally bounded or unbounded powerful. The adversary can be passive or active. And the security that the protocol can give or provide, that can be information theoretic or computational. And similarly, the security that we can obtain can be abort or full security. Now, in this work, we consider an asynchronous network as opposed to the popular choice of synchronous network. Our adversary is computationally unbounded, active, and rushing. And lastly, the security, of course, we receive information theoretic security. In fact, we obtain the perfect security, which is information theoretic security with no error. And we aim for full security, where irrespective of how the adversary behaves, everybody receives the output. So this is our setting. Now let us just understand the difference between synchronous and asynchronous network. So in synchronous network, all messages sent between honest parties arrive within some known bounded delay delta. And in reality, if we set the delta to be too large, then the protocols are going to be inefficient and extremely slow. Whereas if we set the delta to be too small, then we may lose security, or even it can lead to non-termination of the protocols. On the other hand, if you go for asynchronous setting, then each message here sent between honest parties arrives with some finite yet unknown delay. In fact, the adversary can delay the messages between the honest parties, but those messages must eventually arrive. However, with small delays, we have the guarantee that the protocols run really in faster speed. However, we also know that the real-life networks, they are modeled better by asynchronous networks than synchronous networks. Okay? Now, here are a couple of opinions about synchronous and asynchronous protocols from MPC practitioners. The first statement being that asynchronous MPC is much faster than synchronous MPC in particular when the protocol has many number of rounds. Right? This is positive. This is nice. Whereas the other statement is about synchronous MPC. The synchronous MPC has higher security and has less communication than asynchronous MPC. So we want to ride on the first statement. And in this work, we try to close the gap between synchronous and asynchronous protocols. That's the goal. So before going to the result and the communication complexity of the state-of-the-art synchronous and asynchronous protocols, let us just quickly look at the feasibility condition that we need for perfect security with optimal resilience. So we know that any function f can be computed with perfect security in the presence of t less than n by 3 malicious corruption. This comes from the BGW88 work. The same task requires t less than n by 4 corruption when you move to the asynchronous setting. This comes from BCG93. Okay? Now let us look at the gap that exists in the communication complexity between these two classes of protocols. So if you look at the status of synchronous protocols, we see that we already have linear communication complexity in terms of the size of the circuit since 28. So that's BH08, and that got published in TCC 2020. Very recently, in fact, we have given linear time protocol that takes order of d rounds where d is the depth, whereas existing protocols only gave order of d plus n number of rounds at least. Now, if you look at the status in asynchronous setting, then there is a series of works that tried to improve the communication complexity of the protocols. So if you look at the last work, which is the state of the art, here we have a quadratic time protocol. Okay? So we don't yet have a linear time protocol in the asynchronous setting. So an obvious question is as follows. Is there a perfectly secure, optimally resilient asynchronous MPC protocol with linear complexity or not? Or is there an inherent lower bound due to asynchrony? So this is a big question, and this is exactly what we answer in this work. Our answer is positive, meaning that we give the first linear time protocol in the asynchronous setting with perfect security. And this is the statement in details that we prove. And here in particular, you can see that we have linear complexity, and the expected time complexity is order of d, where d is the depth of the circuit. Now, the high-level idea of our protocol. So we try to generate Beaver triplets. That is, these triples ABC in shared format, where ABC are random and unknown to the adversary, and C is A times B. Okay? And then we consume these triples in the online phase in a standard way. As far as how to generate the Beaver triplets, we use a standard transformation, known transformation, which reduces the problem to generating multiplication triples by a dealer. Okay? In this case, this A, B, C will be random and unknown to the adversary only if the dealer is honest, the dealer who is dealing these shares. Now, this problem further reduces to two primitives, the first one being asynchronous verifiable secret sharing, AVSS. And this is essentially, this generates the sharing for A, B, and C. The other building block is what is new to this paper, which is weak binding AVSS. I'll tell you in a minute what that is. It's a weakening of AVSS. And this is used to prove that C is equals to A times B. Okay. And for our work, in order to achieve linear complexity, we need a AVSS that gives order of n cost per secret, whereas for the weak binding secret sharing, we actually need a constant cost per secret. Right? So this already comes from earlier work. However, this was not known, and this is what we achieved using trivariate polynomial as opposed to bivariate polynomials, which are typically been used so far. Okay, so let me just tell you how, what is the difference between AVSS. AVSS is sort of standard. So what is the difference of weak binding AVSS with the standard one? So in asynchronous VSS, as you know, there are two phases, a sharing phase and a reconstruction phase. And the dealer in the sharing phase has a secret which it wants to share amongst a bunch of parties, n parties. And in the reconstruction phase, we want to reconstruct the secret from the shares. Okay, now the properties that we require from this primitive of a VSS are as follows: validity, then secrecy, and finally binding. Most of them are standard, so let me just very quickly repeat them. Validity says that if the dealer is honest, then the protocol must terminate, and at the end of the reconstruction phase, all the honest parties must get the output, the secret. And the secrecy says that the view of the adversary in the sharing phase is independent of the secret. And lastly, the binding, which is the most important one. Here it says that the view of the honest parties at the end of the sharing phase must uniquely define some secret S prime, and the reconstruction of the same unique secret must be guaranteed. Okay? This should hold even if the dealer is corrupt. Now, the difference in weak binding AVSS is actually in the binding property. The rest remains the same. The other two properties are identical. Here in the weak binding, what we require is that the views of the honest parties at the end of the sharing phase must still define a secret, unique secret, but we now don't require the reconstruction of the committed secret or uniquely defined secret, right? So that's the difference. So I want to tell you quickly the ideas that we have used for building this weak binding AVSS protocol. And for that, I have to quickly give you a highlight of the AVSS protocol that was designed in BCG. And I'll just give you the skeleton just so you can understand the new ideas in our protocol. So as per BCG, if you have a dealer then which wants to share a secret S, it picks a bivariate polynomial of degree t in x and y and hides the secret in the constant term of that polynomial. And then there are these n parties to party pi. It delivers s of x comma 1 and s of y comma 1 comma y, where s of xy is the bivariate polynomial that had been chosen by the dealer. Okay. Similarly, the second party gets the evaluation of the bivariate polynomial at 2, right? And likewise for all the other parties. Just in this case, you see that I have taken 5 parties. I mean, because we need 40 plus 1 parties. So if you put t equals to 1, then you have 5 parties. So we have this simple case here. Now, there is a different way to view the bivariate polynomial. You can look at it as a square polynomial, square matrix. So, and the polynomials that are received by the ith party is nothing but the ith row and the ith column of this matrix. Okay. Now, the goal of this AVSS protocol is to generate the secret sharing of the secret of the dealer, which is S, through this univariate polynomial, which is S of 0 comma y. That's a t degree polynomial, and if you look at it carefully, the constant term of that polynomial is actually not is the secret S. Okay. So, in order to achieve this, the parties do the following. So the dealer is supposed to distribute the polynomials this way, but they may not do it exactly in this way. So the parties would do a pairwise consistency checking. So for instance, if you look at party P1 and P2, they have these 2 points in common. So they would exchange these points with each other and verify against the value which has been received from the dealer. And based on that, they're going to broadcast a message, OK or not, right? That's it. So parties will do this pairwise OK checks. And based on this broadcast, the parties will construct a graph, right, where the nodes are nothing but the parties, and there will be an edge between 2 parties if both of them said OK to each other. Right? And once this graph is constructed, the goal is to agree on an n minus t click. In this case, if you have 40 plus 1 parties, then we look for a click of size 3t plus 1. What about the cost of this protocol? The cost of this protocol is n power 4. That's because the parties are doing pairwise checking, and then they're broadcasting these OKs. And every broadcast requires n square cost. And since there are n square pairs of parties, so, and each broadcast takes n square, so it's n power 4. And then you have hidden just a single secret in the bivariate structure, right? So cost for 1 secret is n power 4. And there is another problem here. As you can see, I have assumed finding out a click of size n minus t, so this is inefficient, but we'll deal with it a little later. Just hold on. Now, very quickly, I wanted to argue argue about the properties. So binding, you can see that why it holds is because we are asking for an n minus t click in which the 2t plus 1 parties are honest, and they're all pairwise consistent, and they define a polynomial of degree, bivariate polynomial of degree t in both variables. Now, towards getting a constant overhead protocol, we use two ideas. First is packing, and the other one is batching. So packing says the following, that in one instance, we want to pack many secrets. So for doing that, we increase the degree of the bivariate polynomial in both the dimensions. So before it was t, but now it is t plus t by 2. Right? So that means that one bivariate structure gives us order of n square secrets. And the other the dimension that we use for improving, getting our solution is batching, right? Where we use many instances of the VSS protocol, and the broadcasts are actually done commonly for all. So you do only once for all the instances. Okay, so we run, for instance, n square instances of parallel AVSS protocols, and the broadcasts are the same for all. So we have n square instances, and each instance gives us n square secrets. So that's n power 4 secrets. And the cost of communication remains the same, n power 4, right? And this is how you get constant overhead. Okay. So quickly again, now if we run through the BCG idea with this higher degree, because now we want to pack more, so we have increased the degree of the bivariate in both the dimensions. Earlier it was t, now it is t plus t by 2, right? Does it work? It works as long as you just fall back on the idea of the clique, right? You still have a 3t plus 1 clique in which 2t plus 1 are honest parties, and they will define a unique polynomial of degree t plus t by 2 in both the dimensions. That's fine. But we don't want an inefficient solution. We want to go for a polynomial time solution. So now we'll have to recall BCG, what did they do for getting a polynomial time solution, right? So they suggested the following, that instead of a clique, you try to find out an alternative structure in the graph, which is called star. Now, star is basically nothing but a couple of sets, C and D, where C is a smaller size clique, which is easy to find. And here the size of the clique C is just 2t plus 1. And D is slightly bigger, 3t plus 1, and it subsumes C. And what we want is that every pair of parties between C and D, they must have an edge, right? And the BCG protocol, and in particular the thesis of Canetti, they show that there is a polynomial time protocol, algorithm to find out a star, okay? So that's how they solve this problem. And actually, if you just go back to the idea of BCG, where t-degree polynomial, bivariate polynomial had been used, you will see that everything is fine because C contains 2t plus 1 parties, in which, again, t plus 1 are honest, and they would still define a polynomial of degree t bivariate polynomial. But if you run the same thing for our case, where the degree of the bivariate polynomial has been increased from t to t by 2, it doesn't work anymore because of the same reason. Like we have just t plus 1 honest parties in C, and they wouldn't define a bivariate polynomial of degree t plus t by 2, right? So what essentially seems to be required is a big star, where the C component has extra t by 2 parties. Okay, but then we don't know of any polynomial time algorithm which can find us a big star. So we are stuck. And this is where we transit from bivariate to trivariate. So once we go to the trivariate polynomial, we use the degree t plus t by 2 in all the 3 dimensions. And then every party now will receive 3 bivariate polynomials, and between 2 parties, there will be 6 univariate polynomials to be checked, pairwise checking, okay? And now here is the magical observation. So you still do the OKs, and based on the OKs, you make a graph, right? So the consistency graph, everything remains the same. After the graph, there's this very beautiful observation which comes from another paper. If you take 2 nodes or 2 parties, each of them has degree 3t plus t by 2 plus 1, right? Then you can see that because you have in total 40 plus 1 parties, they will have 3t plus 1 common neighbors, right? And that essentially shows that even though they individually have not okayed each other, there is no edge between them, but just because they have sufficient number of common neighbors, we can say that they are actually consistent with each other. So this is, we call it as transitivity, and this comes from the work of Applebaum and Kachalon in 2024. So, and this is something that we use. And finally, using that, we maintain binding in the following way. We either look for a graph which is dense, meaning that we have a sufficient number of parties who have high degree, and the high degree is nothing but this 3t plus t by 2 plus 1. Or if we don't find such a dense graph, then we actually show how to find out a big star that we were looking for. Right? Big star means the C has this extra number of parties, extra t by 2 parties. And if you observe very carefully, then you will see that both these structures, that is dense graph as well as big star, they ensure that there are at least t plus t by 2 plus 1 honest parties who are pairwise consistent, and they will define this trivariate polynomial of degree t plus t by 2 in all dimensions. So this is the summary slide. So we still use packing, but we use them in 3 dimensions. So you can hide n-cube secrets in one trivariate structure for now. And then we also use batching, and we get this complexity. Order of n square secrets are committed in one with n power 4 communication complexity. So that gives us constant overhead. OK? And that's it. Thank you. And the paper is available there in the link.
Much. Yeah, so we actually don't have time for questions. So we'll have to move on, and you'll have to catch up Peter offline if you have questions. So we'll move on to the next talk, and the slides will hopefully appear in a moment. Hello. Next talk is therefore about fuzzy private set intersection with large hyperballs. This is by Ivan van Basten and Sihang Pu, and Sihang Pu will give the talk.
All right. Thanks for the introduction. Hello, everyone. I'm Sihang, and I'm going to present our recent work about fuzzy private set intersection. It's a joint work with Ivan van Basten. So first, let me briefly explain what is a private set intersection. So here is a traditional definition. Let's assume there are 2 parties, Alice and Bob. Each one has a set. Here is a set of English words or German words, whatever. After several rounds of interaction, after communicating with each other, they would learn the intersection of the 2 sets. Okay, and basically, private set intersection, or PSI, it's a special case of 2-party secure commutation. Here, we typically want a constant around protocol, and we want it to be extremely efficient, not just asymptotic efficient, but also concretely efficient. In general, we want a linear communication and computation costs. So in this talk, I'm more interested in the 2-round PSI. And in our work, we focus on the semi-honest security. In the 2-round protocols, the Alice is going to be the receiver, and Bob is going to be the sender. And semi-honest security means each party will follow the protocol, but still want to try their best to learn the secret from others. Okay, and in the 2-round setting, only the receiver learns the result. The sender, learns nothing of the receiver set except for the set size. Okay, so here I'm going to present you a variant. So what if some letters are mistyped? In this case, let's see, Alice's set is still the same. But what if Bob's set is a letter is mistyped? And because O and I are very close to each other, so it might be mistyped. And a naive approach to resolve or get around this issue is to enumerate all nearby points. Then we can use a traditional PSI. However, by doing this, let's say you add hello, heli, how any words into the set. Your set size is going to be exponentially large, scaling to the radius of the ball. This is actually an example of fuzzy PSI. Fuzzy PSI means each party has a set of points, and these points could be in d-dimensional space. And after interaction, they want to learn if the points are close to each other or not. And here the closeness is defined by some distance function with a threshold delta. And in the end, the receiver would learn the balls intersected by the sender's points. Yes. And in our work, we only consider the exact distance functions. We don't consider to use matrix bannings or any approximations, because both of the two approaches would give you constant rate of the false positive rates or false negative rates. And we consider from L1 distance to L infinity distance. Let me briefly describe some prior approaches. So the most natural one is we can reduce to traditional PSI. We just enumerate the entire ball. We just add each point in the ball to the set. Or we can use generic approaches like Gabor circuits, GMW, or FAG. The drawbacks are with traditional PSI, we're going to have exponentially a blow up. So this is only suitable for tiny balls with small radius and in low dimension space. With generic approaches, because FAG or Gabor circuits have kind of high, can have heavy machinery, so they're only suitable for a small number of points because you don't want to invoke this heavy machinery too many times. And recently, there are some great work by Guthrie, Mike, and Jaspo. So they proposed structure-aware PSI using function secret sharing and bit transfer. So with these two notions, I'm gonna explain later. So in these two works, they achieve the sublinear communication. Here, sublinear means their communication only skew with sublinear to the volume of the balls. But the protocol still have linear computation capacities, which means they need to enumerate each point in the ball. And their protocols are 3-1 protocols, and mainly support infinity distance. And for L1 distance, they require much more expensive operations. And also, they let the receiver learns the precise input of the sender's points. This is not a problem for standard PSI, because for standard PSI or traditional PSI, sender's point and receiver's point in the intersection should be the same. However, in the fuzzy PSI, it'd be different, because you get an approximate match, so there's still difference between your points even in the intersection. For our goals, so first we want a negligible correctness error, which means we don't want any false positive rays or false negative rays. So we want to ask, can we support a large volume, which means we want to support large radius of the ball and also in high dimensional space. And can we support generalized distance, like not just infinite distance, but also L1, L2, and others? And can we support different functionalities apart from standard PSI, but also PSI cardinality, labeled PSI, or even circuit PSI? And of course, we can answer this question affirmatively. So our results are we get a two-run protocol with negligible correctness error. So for two-run protocols, there are some specific applications. For instance, in recent work of illegal content detection, the server wants to publish the first message, or the receiver wants to publish the first message, and this first message is reusable by many different clients. So in this case, two-run protocol is necessary. And for complexity, we achieve a sublinear communication and computation costs. So in low dimension space, we still have a factor 2 to the d, where d is a dimension. But even 2 to the d is still sublinear to the volume. And in high dimensions, we manage to get rid of this exponential dependence on dimensions. And we support generalized distance metrics and also generalized functionalities. You can see it's not just PSI, but also label PSI or PSI cardinality and circuit PSI. Okay, so now let's move to technical part, or a little bit technical part. So first, I want to show you why the prior work doesn't have sublinear computation costs. So they use the function secret sharing, which is kind of like secret sharing, but now you secret share the description of the function. So you share two function shares, f1, f0. The nice property is if you evaluate the same point on the different function shares, you're going to recover the original function evaluation on this point. So in PSI applications, we typically want to secret share a memory test function. So here, memory test function is defined as follows. So the FW, where W is a point set containing every point inside the receiver space. So for now, let's suppose receiver and sender only hold a single point. And if the sender's point is inside this point set, the membership test function would output 0, which means the two evaluation on the different function shares should be equal. Otherwise, they should be different. Okay. Then the receiver can share this membership test function to two function shares, and input these two function shares into a functionality called abyss transfer, which is explained by many works in this session already. The sender selects toss a coin, and going to return the functionality. The abyss transfer will return the function share selected by this bit. Okay, and then two parties just want to determine if the evaluation of a function share 0 and function share selected by sender, if they're equal or not. If they're equal, I mean, if Wi equals to Q, here Wi is a point in the receiver's point set. If they're equal, which means this equation would always hold, no matter what the selection bit is. And this is a basic idea behind the GRS22, and they leverage this idea to construct a PSI, fuzzy PSI, or structure-aware PSI protocol. The problem is, with this approach, the receiver has to enumerate each point contained in this point set. And that's why this linear combination comes from. So we abstract this functionality as fuzzy matching. We call it fuzzy matching. So the functionality is the following. So each party, sender, receiver, each one holds a point in a d-dimension space. The functionality would output a single bit to the receiver. This single bit indicates if 2 points are close or not. Here, the closeness is defined by some distant function with some threshold delta. Here is an example of infinity distance. If 2 points are close enough, which means the difference of projections on each dimension would be smaller than some threshold. Okay. And here I would provide a very brief overview or high-level ideas to of our fuzzy matching protocols for infinite distance. Here is an example in two-dimensional space. The receiver first, the receiver has a point, has a ball centered at the point W, and project on each dimension two intervals, and then the receiver would somehow generate a data structure. This data structure has the following property. So if someone queries the data structure at a point inside this interval, it's gonna return encryption to 0. Otherwise, it's gonna return a random cipher text. And the receiver generates two data structures in this way and sends two data structures to the sender. The sender just query his point in 2 dimensions. For each data structure would return a ciphertext, which could be either a ciphertext of 0 or a random ciphertext. And the sender gonna add them together. So here, we assume the ciphertext is additive homomorphic. The sender sends back the ciphertext to the receiver. Receiver uses a secret key to decrypt it to check if it's a 0 ciphertext or not. So here you can see the correctness always hold, because the 0 ciphertext plus together is always a 0 ciphertext. And to get a sublinear computations, we want this data structure to have the encoding time and the encoding size only depend on the interval itself. And also, the decoding time is constant. Given this, we can get the sublinear complexities. For security, it's a little bit tricky, so please refer to our papers to check the security proof. And yeah, here is a full picture of how we can get a fuzzy PSI from fuzzy matching. The naive way to do this is we do a fuzzy matching for each pair of the points, but it's gonna give you a square blowup. It's undesirable. So we choose to optimize in this ways. So for low dimension space, we use spatial hashing techniques, which is from the prior works. The basic idea is to tile space with many hypercubes, and then you can exploit this geometric structure of the space to avoid this quadratic blowup. And for high dimension space, this factor, I forgot to say there's still factor 2 to the d. This is still too expensive, so we get around this by 2 approaches. We can either assume the receiver's points satisfying some property, then we can reduce the factor 2 to d squared, and while having this linear blowup on party set size, or we can rely on a technique called locality sensitive hash. Then we can reduce the factor from 2 to d to d. But it has a slightly larger blowup. It's subquadratic. Yeah. In summary, I briefly mention our fuzzy matching and how to get fuzzy PSI from fuzzy matching. Please refer to our e-prudent paper for detailed techniques and generalized distance or generalized functionalities. So for future works, I'll leave some open problems, but yeah, we can discuss offline, I guess. Yeah, thanks for listening. Yeah.
Thank you. Any questions? If you have one, go to the microphone up there.
I had a question on the assumption that you rely on. You mentioned additively homomorphic encryption. Is there anything else?
You mean okay, for assumption, we only require DDH. Yes.
DDH for the additively homomorphic encryption?
Actually, yes, and not just for that, also for the data structure I mentioned before.
I
yeah.
see.
Yes.
Thanks.
Yes. Any other questions? I was wondering, of all these distances that you can handle, are they all L something, or are there other things as well, like maybe edit distance?
Yeah, it's a good question. So we thought about that, but It seems edit distance a bit hard to get, but Hamming distance is achievable, yes.
Okay, good. Anything else? Okay, let's thank the speaker again. Yes, we will go to the next talk. The final talk of this session is on fast public key, silent OT, and more from constrained narrow wrangled. This is by Dong Bui, Geoffrey Couteau, Pierre Meyer, Alain Pasadek, and Majid Riahinia. And Majid will give the talk.
Yes, thanks for the introduction. Hi everyone, I'm Majid. So let's get started. So in our paper, we consider a recently introduced notion in the context of secure computation, which is pseudo-random correlation functions. So let's see the definition. Okay, pseudo-random correlation functions, or PCFs, they were introduced by Boyle, Couteau, Gilbay, Shai, Cole, and Scholl in 2020 as a way of generating correlated randomness on demand. So in this protocol, we have two parties. And then there is this central key generation algorithm that generates two keys and gives each of them to one of the parties. And then whenever these parties want to generate some correlated string together, they're going to locally use their keys to run some evaluation algorithm on some common input X. And these two outputs are required to be correlated to each other in some way. For instance, useful correlation, especially in secure computation protocols, is oblivious transfer, or OT for short. And if we have a PCF that generates OT-correlated random strings, then the two outputs will look like this. So one of the parties outputs two random strings, R0, R1, and the other party outputs a random bit B and the corresponding string RB. Okay. Of course, there's also a notion of security involved, which is basically what the correlation imposes. Okay, so for instance, for the case of oblivious transfer correlations, we want the party that generates the two random strings to have no idea about the bit that the other party generates, and we want the other party that generates the bit B and the string RB to have no idea about the string that it couldn't generate, so about R1 minus B. Okay. Now, in our work, we show how to make this thing, so a pseudo-random correlation function for OT correlation specifically, that is both very efficient and also is public key. And by public key, what I mean is that instead of the central key generation algorithm, we have a public procedure that allows these two parties to derive their evaluation keys non-interactively or publicly. Okay. So here's how we do it. We show how to make an efficient public key PCF for OT correlations from some version of the narrow-wrangled pseudo-random function that we call narrow-wrangled constraint pseudo-random function. I'm going to define it later, but for now, here are the steps that we take to achieve our results. So we're going to start from the narrow-wrangled pseudo-random function, and we're going to show that applying a slight modification to this construction will give us a useful variant of pseudo-random function that we call pseudo-randomly constrained PRF. I'm going to define it in a minute, but for now, in the next step, we show that if we have this pseudo-randomly constrained PRF, then we have a generic transformation that can give us PCF for OT correlations. Okay? And finally, what we show is that if we instantiate this PCF for OT through all these steps, so from the narrow-wrangled pseudo-random function, then we can upgrade it to be public key and so to allow the non-interactive generation of evaluation keys. So we have public key PCF for OT from narrow-wrangled. We also show some applications of public key PCF for OT in reusable designated verifier non-interactive zero-knowledge proofs. But for now, in this talk, I'm going to focus on these three first steps. And I'm going to start by this transformation in the middle. So how to get PCF for OT if we have this variant of pseudo-random function, pseudo-randomly constrained PRF. So let's see the definition of a constrained pseudo-random function for now. So a constrained pseudo-random function is a pseudo-random function. So it uses some random associated key to generate some outputs that look random. But it has an additional feature compared to normal pseudo-random functions, which is that for a subset of inputs like S, you can use the mass-sophisticated key to generate a partial key that's called the constraint key. And anyone that has this constraint key, but not the mass-sophisticated key, can use it to evaluate the output of the function on this subset of inputs S. Okay? So basically, this constraint key evaluates the same thing as the mass-sophisticated key on all the inputs that are inside this subset S, and everywhere else. So the output of the function on inputs outside of this subset should still look random, even given this constraint key. All right. The final thing that I want to say about constraint PRFs is that this subset on which we can do this constraint evaluation is usually defined by a predicate. And basically, any predicate F, for instance, can define such a subset in this way. So we consider the constraint subset associated to F to be all the inputs where F evaluates to 0. Okay? And then we call the constraint key that enables us to evaluate only on this subset by CKF. Now, an interesting choice of predicates, especially in our work, is when this predicate itself is random. Okay? So basically, when this predicate is random, then the subset that it defines is also random, right? So we have a CPRF that can generate a constraint key to evaluate on a random subset. Then we call the constraint PRF a pseudo-randomly constrained PRF. Okay? So it's the definition of pseudo-randomly constrained PRF. And now that we know it, let's see the transformation of how we get PCF royalty if we have this. Okay, so we have our two parties. And what we need for our transformation first is a weak pseudo-random function, which is also a predicate, so it evaluates to 0 or 1 on any given input. And a constrained PRF, which is basically a pseudo-randomly constrained PRF. So it should support FK. I consider the key of the PRF to be K. And the CPRF should support FK and also its complement. What I mean by this is that we want a CPRF that can generate a constraint key for either of these two sets. Okay, so either all inputs where F evaluates to 0 or all inputs where F evaluates to 1. So the important thing to know here is that we don't want a CPRF that generates two keys for each of these sets, or for both of these sets. We just want a CPRF to be able to generate one constraint key, but we want the flexibility of being able to generate it for either of these sets. Okay. So if we have these two things, here's what we do. The key generation algorithm is going to simply generate two mass-sophisticated keys for the constraint PRF and give them to one of the parties. And then it's going to use these mass-sophisticated keys to generate two other constraint keys. Two constraint keys, give them to the other party together with the weak PRF key K. Okay? So what are these two constraint keys? The yellow constraint keys is a constraint version of the yellow mass-sophisticated key with respect to FK. Which basically means that it evaluates the same thing as the yellow mass-sophisticated key on all inputs where F evaluates to 0. And the black constraint key is for the complementary set. So it evaluates to the same thing as the black mass-sophisticated key for all inputs where F evaluates to 1. Okay? So we have our keys. Now here's how they compute their share of correlated randomness. So the user with the two mass-sophisticated keys is going to just simply evaluate the output of the CPRF on input X using the two keys. And the other user, so the one with the two constraint keys, is going to first evaluate the output of the weak PRF on input X. So it generates some bit, 0, 1, and then depending on this bit, it's going to use one of the two constraint keys to evaluate the output of the CPRF on X. Okay? If the output of FK on X is 0, it's going to use the yellow constraint key, and otherwise it's going to use the black constraint key. What we claim here is that these two outputs are indeed OT correlated. Okay? Basically, the one on the left is composed of two random strings, or 0 or 1, and the one on the right is composed of a bit B, a random bit B, and the corresponding string RB. So why is it the case? First of all, the two strings R0, R1 are outputs of a constraint random function, right? So they do indeed look random. And bit B is also the output of a weak random function, so it also looks random. Okay? So why is RB of the correct form? Let's consider an input X on which FK values to 0, in which case the party on the right-hand side uses the yellow constraint key. And remember that the output of the CPRF on X using this yellow constraint key is the same thing as the output of the CPRF using the yellow message ticket key on this input, because it was generated with respect to F. So indeed, in this case, this party outputs 0 and R0. And for an input where FK values to 1, this party is going to use the black constraint key, but kind of the same thing happens. So here, the output of the message ticket key on X using the black constraint key is the same thing as the output of the CPRF using the black message ticket key on this input. So that's why, in this case also, this party correctly outputs 1 and R1. Okay? So indeed, these two outputs are OT correlated. Now for the security, remember that the bit B that the party on the right-hand side generates is the output of a weak pseudorandom function, right? And the key of this pseudorandom function, yeah, it's hidden from the point of view of the other party. Okay, so indeed, this bit B looks random to this party. And for the security against the other party, we just have to notice that for any input X, one of these two constraint keys fail, okay? And it not only fails to compute what the other message security computes, but it even doesn't help in distinguishing the output of the message security on that input from random, okay? So the security against this party is also basically holds from the security of the underlying CPRF, okay? So the construction is also secure. It also satisfies another property that's called pre-computability, which is useful in the pre-processing model in secure computing protocols, which basically says that this party on the left-hand side with the two message secret keys can generate its own keys locally and evaluate its share of the correlated randomness way before even knowing the identity of the other party, right? It's not depending on anything that the other party has. Okay, so I just told you about the transformation of getting a PCF for OT that's also pre-computable from pseudo-randomly constrained PRF, which is basically a CPRF that supports weak PRFs and their complement. So I'm going to quickly go over the previous step, showing how to instantiate this pseudo-randomly constrained PRF from Damgård. What we actually show in our paper is a bit more general than that. We show that if we apply a slight modification to the Damgård pseudo-random function, then we can get a constraint pseudo-random function for inner product membership predicate. So basically, the constraint set can be described by an inner product membership predicate. And then the link between these two, so between having a CPR for inner product membership and CPR for weak PRFs and their complements, is made by observing that we have a lot of weak PRFs in the literature that can be expressed as inner product membership predicates. Okay? So let's see how we make constraints random function for inner product membership predicates from Damgård. So here's a brief overview of the Damgård random function. It's very simple. So the message secret key has only a group element G and n exponents A1 to AN. And when we want to evaluate the output of the PRF on some binary string X, we're going to simply multiply AI to the X size and then raise G to the power of the result. So it's quite simple, and it's very low complexity. It can be computed by an NC1 circuit. And the security is based on a decisional Diffie-Hellman assumption. OK, so I will first tell you how to generate a constraint key for inner product, meaning that if we have a vector Z, which is binary again, then how to generate a constraint key that can evaluate on all inputs that are orthogonal to Z. Okay? So here's how we generate the constraint key. We're simply going to put the base G and some randomized exponents AI times R to the minus EI for some random element R. And then when we want to evaluate the output using this constraint key on some input X, we're going to simply use this randomized exponents in the same way as before, though. Okay? And then if we write it beautifully a bit, you're going to see that the output of the constraint key is the same as the output of the massachusetts key if the input X is orthogonal to Z. Okay, for the security, I'm not going to go into much details about it, but the security in the case where in the security game we don't let the adversary to have access to the evaluation oracle holds basically unconditional. And then we get the full security, so adaptive and with any number of evaluation queries by hashing the output of the function using a random oracle. Okay, so now let's generalize it and generate constraint keys for inner product membership predicates. So here I'm going to have a vector Z and a subset S. And I want to be able to generate a key that can evaluate on all inputs X if X times Z falls in S. Okay? So the constraint key kind of has the same shape as before, but instead of only giving G, I'm going to give more elements with respect to set S, G to the R to the S, for different members of the set, but the same randomized exponents. And then when I want to evaluate the output of the function using this constraint key on some input X, I'm going to use one of these elements, G to the R to the S, in the same way as before, though. And then if there exists some element in the set where X times Z is equal to it, then the output of the constraint key is going to be equal to the output of the master secret key. Okay, and for the security, again, the no evaluation security is going to happen because of an assumption that we introduced in our work, and we call it sparse power DDH assumption, which is basically a generalization of the power DDH assumption, if you're familiar with it. And then we get the full security in the random oracle model by just hashing the output using a random oracle. Okay, just a quick mention of the inner product membership predicates. Actually, it turns out that this set covers more than one might expect. Inner product membership predicates include inner product equality and inequality predicates. It also captures some notions of puncturing, and in particular, our construction also yields a puncturable PRF in NC1. More importantly, for our work, inner product membership predicates also capture some constructions of weak random functions in the literature, namely the ones from the learning with grounding assumption and the one that we call XOR match, who is basically from Goldreich's one-way function. Okay. So, yeah, I told you about the first 3 steps of how we get our results. In our paper, we also do a lot of optimization on each of these steps, so we get the efficiency. That's it. Thanks.
Thank you very much. Any questions? Yeah, so this might be a stupid question, but so you said that you can have weak PRFs where membership can be expressed just by inner product being 0, right? So then why was the inner product thing not enough? Why would you need the set S at the end there?
I don't know. So I mean that it's really inner product membership predicate. Like we need a set S that's actually public. Yeah. For instance, I included this construction, and this set S is a set indeed. It's not just an element.
All right. So it would have been enough if the membership you were after were just inner product being 0. But
True.
Inner product being in some set.
Yeah, indeed.
Okay.
Yeah.
Anything else? Okay. In that case, let's start.